Okay, so in the previous lecture, we had introduced the concept of continuous functions on an arbitrary topological space. So let us discuss a few examples which might be a bit relevant examples. The first example we will do will seem a bit nostalgic. Let f we consider a function f which is real valued and defined on the real numbers as well. Let x naught be an element from R and let epsilon be a positive number. Let V be this interval fx naught minus epsilon, fx naught plus epsilon. Okay. Now this is relevantly an open set, right? Open set in R. Obviously, since we have not discussed about any specific topology on R, so we are obviously working with the standard topology, and this is an open set with respect to the standard topology. So yeah, so it's an open set, right? Now, what is f inverse of V? So it's the set of all elements x such that fx is in this interval, right? It's in the interval fx naught minus epsilon, fx naught plus epsilon, right? So it is obvious that x naught is then in f inverse V, right? Because fx naught is in this interval, right? So this is basically an interval. If you consider this as a ball, so it's a linear ball. If I be very, it's with a slight abuse of language, it's a linear ball with the center at x and the radius epsilon, right? Because it is constructed from x naught with epsilon distance on its right and epsilon distance on its left. So x naught is obviously in this interval, and that implies x naught is in this set because fx naught is in this interval, right? So x naught is in the inverse image of V, right? Now suppose f is continuous. Suppose f is continuous. Okay. Then f inverse V must be open, right? So if f inverse V is open, then that implies that there exists a basis element. What is the basis element of the standard topology? See, these are the open intervals AB, right? We obviously consider the standard topology. It's also called the ordered topology. The standard topology is also referred to as the ordered topology because these intervals are completely based on a specific order defined on R, which is symbolized as the less than equal to, right? So there is a basis elements AB about x such that AB is contained in F inverse. Is it clear? So yeah, is this clear? So there is the basis element AB about x which is contained in this F inverse V. Since F inverse V is considered to be an open set. Okay. Now if I choose A to be, so let A to be this interval. So let A to be x naught minus delta, B to be x naught plus delta. Then that would imply this interval AB is nothing but x naught minus delta, x naught plus delta interval, right? For some positive number delta. For some positive delta. But doesn't this immediately imply that therefore, whenever an element x is inside this interval x naught minus delta, x naught plus delta, then doesn't that imply that x must be in the interval? Sorry, fx must be in the interval fx naught minus epsilon, fx naught plus epsilon, right? Right? And this was our exact definition of continuous functions over R, right? We said that for all epsilon greater than 0, there exists some delta greater than 0 such that whenever mod of x minus x naught is less than delta, which is precisely saying that x is in the x in this is in this interval. This would imply that mod of fx minus fx naught is less than epsilon. So fx is in this interval, right? So this was our precise definition. The converse is quite trivial to see. There is nothing much constructive about that, right? So this is what we also call the epsilon delta definition of continuity, right? I guess it's clear. Okay. Have you not understood why this happens? This is from exact definition of what basis is, right? What is the condition for a topology to be generated by a basis? There is a definition which I gave in the previous lecture, I guess, that if you choose any element from an open set, suppose x u is an element from tau, if you choose any element from an open set, then there exists a basis element such that x is in this basis element and this basis element is completely contained in the open set. That is what we have applied here. So this F inverse V is an open set in R, right? So if I choose any element from F inverse V, which is x naught here, then there must be a basis element which is AB, but x is in AB. That is the meaning that AB about x. So x is in AB and AB is contained in F inverse V. So it must be, yeah, it must be contained in F inverse V. Correct. Got it? Clear? Okay. Like, so if I consider a few examples of continuous functions, few very trivial examples of continuous functions. Let's say, let us first consider a very specific function. Okay, that how are continuous functions. So in the previous lecture, I had always emphasized about the fact that continuous functions are completely determined by the topological structure of the domain and the codomain on which the function is defined. So let us get a example to have a viewpoint on that. So let R be the reals with standard topology. Okay, and RL be the reals with the lower limit topology. So what is the lower limit topology? This is the topology which is generated by the half open, half closed rays, right? Generated by these sorts of elements, right? But we had also previously discussed these. What is the lower limit topology? On our, I guess it's in the open and closed sets lectures. I'll give every lecture on topology, you know, in the description box of this video. You can view from there. Okay. So the topology which has basis elements of this form. These are the where A and B are from DLs. Okay. So if I consider a mapping F from R to RL, let's say, and let F be the identity mapping, Fx equals to x. Right? Is F continuous? Is F continuous? What should be the answer? So it's just the identity mapping, right? What is F inverse of AB? This, the basis element. It should be AB. Closed open B. Now, closed A open B is open in RL. By the way, RL is the topology on RL is constructed. But the inverse mapping of open, the inverse mapping of inverse image of the closed A open B interval is an interval in R, and R we have considered standard topology. Is a half open half closed ray a half open half closed interval open in the standard topology? It's not, right? In standard topology we have the basis elements as open intervals AB. So these elements are not open with respect to standard topology, right? This is not open with respect to standard topology, not open in R, right? Therefore F is not continuous, right? Because for F to be continuous, we need to have the fact that inverse images of open sets must be open. This is not happening here quite. But what if we define f from RL to R by the same mapping. Let f be a mapping from RL to R such that same mapping, identity mapping. In this case, observe that what is f inverse of open interval AB? It's the open interval AB, but the open interval AB is open in RL. And why is it so? Because RL is finer than R, or I should be specific about the fact that because tau L is finer than the standard topology. This is the lower limit topology. Okay. What is meant by the word finer? It's simply contained. Okay. Tau is said to be a finer topology, than tau dash if tau dash is contained in tau. That's it. So the topology generated by the open intervals is completely contained in the topology generated by the half open, half closed intervals. That's it. Right? So therefore, so since tau dash is contained in tau, or here in this case, if I relate the fact, so tau standard is contained in tau L. Therefore, every open set with respect to the standard topology must be an open set with respect to the lower limit topology, right? So in this case, f becomes a continuous mapping. So here f is continuous because the inverse mapping of every open set in R must be open in RL, because open sets in R are also open in RL, because the standard topology is coarser than the lower limit topology. Coarser is opposite of finer. So tau is said to be finer topology than tau dash if tau dash is contained in tau. So tau dash is said to be coarser than tau if tau contains tau dash. So the subset is coarser and the superset is finer. That's the precise logic. Okay. That's the precise logic. Yeah. Yeah. So a few specific examples, if I say examples. Number one. Suppose you consider a three variable real valued function. That is a mapping f from R3 to R. It's always continuous. Okay. A mapping. Okay. A mapping f from R to R2, which denote the curves on a plane. These are continuous mappings. So two. If you consider vector fields in a plane, that is a mapping from R2 to R2. These mappings are called vector fields in a plane. These are also examples of continuous mappings. Okay. Yeah, so we have discussed a lot about continuous functions. Let us just discuss a few properties of it, or theorems related to it. Okay. Theorem. Let x and y be topological spaces. Let x and y be topological spaces. And let f be a mapping from x to y. Then the following are equivalent. Statement number one, f is continuous. Statement number two, for all a in x, subsets of x, the image of the closure of A is contained in the closure of the image of A. Okay. Number three, for all closed sets B in Y, F inverse of B is closed in Y. Okay. Sorry, closed in X. And number four, for all small x in capital X and each neighborhood V of Fx there exists a neighborhood U of X such that the image of U is completely inside V. Okay, so let's explore each of these properties one by one. Okay, so the proof number one. So what first we do, one implies two. Okay, yeah. So let's start with an element from A closure. So let A be a subset of X and let X be an element from A closure. Then what do we need to show? We need to show f of X is contained in f of A whole closure. Right? This will do. Because if this happens, since X is arbitrarily chosen from A closure, then this would imply that f of A closure is contained in f of A whole closure. Right? That is what we actually need to show. Okay. How do we do this? Okay. We choose a neighborhood V of fx. We need obviously we need to make use of the fact that f is continuous, right? Let V be a neighborhood of fx. That implies that basically implies V is open. Right? So that implies f inverse V is open in X. Is open in capital X. And since V is a neighborhood of fx, so X obviously belongs to f inverse V. Right? This is exactly what we said in the while having discussion on the epsilon delta definition, right? That if you consider a neighborhood of the point fx naught, then x naught must obviously be inside the inverse image of the neighborhood. So x is in f inverse V. Now if x is in f inverse V and x is an element from A closure, right? Since f is continuous, so we have already written that f inverse V is open in X. X is in f inverse V. So therefore f inverse V is a neighborhood of X, right? There is a neighborhood of X, right? Now since X belongs to A closure, what is the definition of a closure point or an element of the closure of a set? Every neighborhood of that point must intersect the set A, right? Therefore, every neighborhood of X must intersect A. In particular, f inverse V must intersect A, right? So f inverse V intersection A is non-empty, right? So that means there is some non-zero element, or rather there is some element in f inverse V intersection A, right? Therefore, let Y be an element from f inverse V intersection. But if Y is an element from f inverse V intersection A, then doesn't that immediately imply that V intersection FA is equal to Y? Right? Right? So yeah, so if V intersection FA is equal to Y, yeah, let this be the singleton set. But doesn't that immediately imply that f of x is then contained in f of a whole closure? Why is it so? Because, or if we can simply write it, which will be more relevant according to definition, that then V intersection fa is non-empty from this, right? I guess this should have been fy. Yeah. Sorry, this should have been fy. So if y is in this, then fy is in V intersection fa. Yeah, right. So therefore, V intersection fa is non-empty, to be very specific. But if V intersection fa is non-empty, then that means, and V was an arbitrary neighborhood of fx. That means every neighborhood of fx must intersect f of a, right? Fx is an element from f of a, since x is an element from a closure. right? Or sorry, or X is an element, yeah, X is an element from A closure, and Fx was the image of X. So Fx is an element from Y, right? Fx is an element from Y. Fx is such an element such that every neighborhood of Fx intersects f of A. Therefore, Fx is a closure point of f of A. Closure point means elements in the in the closure of the set. Therefore, Fx must be in the closure of f of A, right? And that immediately implies that f of A closure is contained in f of A whole closure, right? Okay. So next, what we do is we prove, say, 2 implies 3. Okay. Let's prove 2 implies 3. So what is the third statement given? The third statement given is that for all closed sets, the inverse image of closed set is closed as well. Okay. Let B be closed in Y. Let B be closed in Y. We need to show that F inverse B is closed in X. We choose A to be F inverse B. So we need to show A is closed in X. Okay. That is to show A is closed, right? Which implies that the closure of A equals to A, or we can simply prove that the A closure of A is contained in A, because by definition A is contained in A closure. Because remember, the definition of A closure is the intersection of all the closed sets containing A. So A is trivially inside the closure of A. To show that they are equal, we just need to show the closure of A is contained in A, right? So let's try and prove that. So we have chosen that A is equals to F inverse B. Then what is F of A? F of A is F of F inverse B, right? But that should be contained in B, right? Right. Now let X be an element from A closure. To show that X is in A. Then what is F of X? So F of X must be contained in F of A closure, since X is contained in A closure. But using the second statement, we have that F of A closure is contained in F of A whole closure. But F of A is contained in B, so F of A whole closure must be contained in B closure. But B is closed, so B closure must be equal to B, right? So this happens because X is in A closure. This happens from statement 2. This happens since F of A is contained in B, and this happens since B is closed. Okay. But that immediately implies that X is contained in F inverse B. And what is F inverse B? It's equal to A. That implies A closure is contained in A, which implies A closure is equal to A. Therefore, A is closed. Right? Therefore, A is closed. Okay. Therefore, eventually we have proved the fact that if F is continuous, then inverse images of closed sets are closed. After we have proved the equivalence completely, that is the complete theorem, then we can eventually say that if, like in case of the definition of a continuous function, if inverse images of open sets are open, then the function is continuous and converse. Here also we can say the same fact that like if inverse images of closed sets are closed, then the function is continuous, and if the function is continuous, then inverse image of closed sets are closed. Right? Okay. Now we prove 3 implies 1. Okay, we prove that 3 implies 1. So let B be closed in Y. This is very easy to see. Let B be closed in Y. Then that implies Y minus B is open in Y. Right? Right? So we need to show that F is continuous. We need to show that F is continuous. Okay? We can do it not in this form. We need to use the fact that inverse images of closed sets is closed. Yeah. Let B be closed in Y. Then that implies F inverse B is closed in X. This is what we need to show. Observe that since B is closed in Y, then that implies Y minus B is open. is open in Y. Consider F inverse of Y minus B. F inverse of Y minus B is specifically X minus F inverse B, right? We need to show that this is open. Since B is closed in Y, by the third statement, F inverse B is closed in Y. But that immediately, sorry, F inverse B is closed in X. But that immediately implies that X minus F inverse B is open in X, right? And therefore, F is continuous. Because so what is X minus F inverse B? So it's basically F inverse of Y minus B, right? Y minus B is open in Y, which automatically implies the fact that X minus F inverse B, or its inverse image of Y minus B, is open in X. So it's continuous, right? Okay. So now we are just left with the fourth statement. Let's first go back to the fourth statement first. Let me just add one thing to the fourth statement. This is actually the definition of continuity at a point. Continuity at a point X. That is, if I just remove this term for all X, then I can say that the function is continuous at some point small x in capital X if each neighborhood V of fx, if for each neighborhood V of fx there exists a neighborhood u of small x such that f of u is contained in. Okay. So let's start with proving 1 implies 4 and then we show 4 implies 1 as well. So 1 implies 4. Now this is obvious because if f is continuous, then choose an element capital X, small x from capital X, and our usual coursework that we choose V to be an a neighborhood of, or open neighborhood of f of x, and let V be a neighborhood of fx, open neighborhood obviously, open neighborhood of fx. But that means f inverse V is open in X because f is continuous. Now obviously it's a subset of X, so let U be f inverse V. But this implies what is f of U? So it's f of f inverse V, and that should be contained in V, right? That this is usual operations of functions. Let us show how 4 implies 1. So let V be open in Y. Let V be open in Y. Let X be an element from f inverse V. Then that obviously implies fx is contained in V. Now 4 is true, right? Therefore, there exists a neighborhood ux of x such that f of ux is contained in V. But that implies ux is contained in f inverse V. But then f inverse V is nothing but the union of all these ux. Each of these ux are open intervals because they are neighborhoods of x. I mean open sets because they are neighborhoods of x. So arbitrary union of open sets is open. So that implies f inverse V is open. Right? And that's what we exactly need to prove. Is it clear? Is it clear? I guess it's clear. Right? Okay. In the previous lecture, we had introduced one more important terminology. That was the concept of a homeomorphism. So let us also check a few examples of homeomorphisms as well. So, okay. Example. So what was the homeomorphism? So it was a mapping between two topological spaces such that it's bijective, it's continuous, and the inverse function is also continuous. Right? Homeomorphism is important in the sense because if there exists a homeomorphism between two topological structures, two topological spaces, then their topological structure is same, or their topological structure is equivalent. And the homeomorphism is kind of an analogous concept to what we say isomorphism in linear algebra. Okay. Now observe some trivial facts. Let f from x to y be a injective continuous map. Okay. If you restrict the codomain y to the range of this function f, then f becomes bijective. Therefore, if z is considered to be the image of x, then the same mapping from x to z is continuous and bijective. Right? Is continuous and bijective. Now, if f dash is a homeomorphism of x with z, then we say or let us do one thing, let us not use the same notation of f, let us use it as f dash, yeah, because we need to restrict f to this range, right? It won't cause a problem though. It typically won't cause a problem. We can consider it to be the same image f. Yeah, it will do. We don't need a restriction because we are doing nothing with the domain, right? Okay. Then if f is a homeomorphism of x with z, then we say that f is a uh, topological embedding or basically embedding of x into z, sorry, x into y. So what is basically done here? So basically, if you have a, so in the previous lecture as we had discussed that homeomorphism typically implies that the two topological structures are equivalent, right? Therefore, if you have a homeomorphism between a topological space x and the image of the function f, which is contained in some topological space y, then the complete topological structure of x is somewhere can be considered to be within the topological space y because of this homeomorphism, right? That is, if suppose this is x, we map it to f of x, we say this is a homeomorphism, but that means both of them have similar topological structure. Tau x is similar to tau of fx, let's say. So fx is basically a subspace of y. So fx is contained in y. Therefore, fx, so x can be typically considered to be a subspace of y due to this homeomorphism, and hence we say that x is embedded into y. Okay, that is the precise thing. Clear? Okay. So let's check a few examples. So this was an example number 1. Example number 2, which is very trivial. Let f be a real valued function defined on R such that fx is equals to 3x plus 1. Then obviously it's a continuous function, it's a polynomial function, it's a continuous function. It's 1 1, which is very obvious. It's onto as well. Again, that is also pretty obvious. So it's a continuous bijective mapping. What is f inverse of x? F inverse of x is y minus 1 upon, sorry, x minus 1 upon 3. It's again a, you can consider this to be a rational function, right? So it's x minus 1 upon 3. If you consider 3 to be a constant function, x minus 1 in the numerator is obviously another polynomial function. So it's a rational function with a non-zero denominator. So it's again a continuous function. Continuous function over R, right? So f is obviously a homeomorphism, right? F is a homeomorphism. Clear? One second. Okay. Next, let us consider, suppose let's say f is a mapping from the open interval -1 to 1 to R, such that f of x is given as x by 1 minus x squared. Okay, then this is also a homeomorphism, right? This is also a homeomorphism, because obviously 1 and -1 are both not included in the domain, right? So the the denominator is a non-zero polynomial. The numerator is also a polynomial, so it's a rational function. Therefore it's a continuous function. It's 1 1, obviously. It's quite trivial to observe. It's 1 1, because if you consider the set of elements which map, okay, if you consider 2 f of x1 to be equals to f of x2, then what do you get? So you get x1 by 1 minus x1 squared is equals to x2 by 1 minus x2 squared, right? From here you can obviously come up with the fact that x1 must be equals to x2, right? It's also onto by definition, because every element of the form x minus 1 minus x squared in R has an element x in R, such that x can be mapped to x minus 1, x by 1 minus x squared. So it's onto as well. One more way of just checking that it's bijective is by just considering an inverse mapping, which is fairly, you can say, by hit and try, or by just observing the function. You can consider f inverse x to be of this form, right? 2x upon 1 plus 4x square to the power 1 by 2. It's an inverse mapping of f, and it's again continuous, right? So this again gives you a homeomorphism. Okay, very clear. Let us consider a few examples of continuous functions on a general note. Okay, or how can we construct continuous functions by observing the topological spaces. So let us consider this topic as constructing continuous functions. I won't go into much details of why they are continuous functions. I'll kind of leave them as an exercise, but I'll give some necessary hints whenever required. Number one, okay, let me introduce three topological spaces. Let X, Y, and Z be topological spaces. Then the following are always continuous. Then the following are always continuous. Number one, f from x to y such that f of x is equals to y naught. So it's a constant function, right? It's a constant function. Y naught is a constant from y, or it doesn't vary with x, right? For all x in x, and y naught is fixed. It's a continuous function. An obvious hint, I would say, would be just to observe what is the inverse image of any open set in Y. So it's of the form, so it will be the whole of x if y naught is in V, if y naught is in V, and it will be the empty set if y naught is not in V. In either cases, x and phi both are open sets, right? So if inverse V is always open, provided V is open. So that's quite obvious to observe. Number two, let A be a subspace. Let A be a subspace of X. Then we consider a mapping which is called the inclusion mapping, which is kind of including the elements of A into X. You might think of it like that. So let A be a subspace of X, then consider the map J from A to X is continuous. Okay. Why is it so? Why is it so? It's any arbitrary mapping. Any arbitrary mapping from the subspace to the whole space. Why is it continuous? A simple hint would be, if you consider any open set from X, let U be open in X. what is J inverse U? So it's U intersection A, right? Because kind of we are just restricting the image of U to A. So the inverse image of U will contain elements from X as well, but we are restricting to those elements which belong to A. So the inverse image of U must be elements which belong both to U and A. So it must be U intersection. U is an open set in X. A is a subspace of X. So U intersection A, these elements are open in A by the definition of a subspace topology. So J inverse U must be open, right? That means J is continuous, right? Number 3, let's say, yeah, this is very obvious because if f from X to Y is continuous and G from Y to Z is continuous, then the composition map G of f from, yeah, it's from X to Z is also continuous. Why is it so? If you choose an element from Z which is open, let yeah, let lambda be open in Z, then that implies G inverse lambda is open in Y because G is continuous. But that implies f inverse of G inverse of lambda is open in X as f is continuous. But f inverse G inverse of lambda is nothing but G of f inverse of lambda by the definition of composition function is open in X. So we started with an open set in Z. We find that the inverse image of that open set with respect to the composition function G of f is open in X. So that typically means G of f is continuous, right? Let us go for number 4. Let A be a subspace of X. Let A be a subspace of X and f from X to Y be continuous. Then if I restrict this function to the subspace A, then f subscript A from A to Y, where fa is nothing but the restriction of f to the subspace A, is again continuous. Okay. Why is it so? Because we can use the concept of the inclusion mapping here. We know that there is a mapping from A to X which is continuous. So this is the inclusion map. And we are given that f from X to Y is continuous. Then we consider the composition of f and this inclusion map, right? There is a mapping from A to Y, right? And it should be continuous from statement 3 because f and j both are continuous. But what is f of j? This is nothing but f restricted to A, right? By definition. So in case of f of j, we only deal with those elements of X which are inside the subspace, and it exactly behaves like f, nothing else, right? Is it clear? Okay. The restriction function also is a continuous function. Let us go to two more such constructions. Number 5, let's say, okay, let f from X to Y be continuous. Let Z be a subspace of Y. If Z, if Z is a subspace of Y such that f of X is contained in Z, then a function g from X to Z is continuous. Okay. Similarly, if Y is contained in Z such that Y is a subspace, then a mapping H from X to Z is continuous. How is it so? We again need to use statement 3, composition function. How can we do this? See, f f from x to y is continuous, right? F from x to y is continuous, right? We say that Z is a subspace of Y which contains f of x, right? So suppose let B be open in Z. Let B be open in Z, right? Then since Z is a subspace of Y, so B is of the form say Z intersection U, where U is open in Y, right? Now, what is F inverse of U, right? Then F inverse of U must be equal to G inverse of B, right? 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 Now, F inverse of U is open because F from X to Y is continuous. Then G inverse of B is open also. And B is a open set from Z. So its inverse image is open in X. So F from G from X to Z is continuous, right? And the other side is typically proven because it is this part is exactly what we had stated in number 4. Because if Y is a subspace of Z, then just consider the so X from F from X to Y is continuous. We can consider the inclusion map from J to Z because Y is a subspace of Z. So just consider the composition J of F. That will do. Right? Right. Okay. And the last such construction we will leave as an example. Sorry, we will leave and completely leave as an exercise. I think it should be easy to show. F from X to Y is continuous. If X can be written as the union of open sets U alpha, such that f of U alpha is continuous. Sorry, f restricted to U alpha. F restricted to U alpha is continuous for each alpha. Try it out. So, okay, so we end this part with a very important theorem, or I should say a lemma related to continuous functions. Two important theorems, I should say. So we just state them. The one is called the pasting lemma. What is the pasting lemma? Let X is equals to A union B, where A and B are closed in X. Let F from A to Y and G from B to Y be continuous. If Fx equals Gx for all x in A intersection B, then F and G so you can say that so if Fx equals to Gx for all x in A intersection B, then F and G gives rise, we can say simply it gives rise to a continuous function, h from x to y, such that h can be defined as fx when x belongs to A and gx when x belongs to B. Okay. what can be a quick proof of this? Okay, so we are simply consider a closed set in Y. Let C be closed in Y. Okay. What is S inverse of C? It's obviously F inverse C union G inverse C, right? Now F is continuous, so this is closed. G is continuous, so this is closed. Union of two closed sets is closed till it's a finite union. It's obviously a finite union. Therefore, H inverse C is closed, right? You can write the statements of the proof on your own. Okay. And one more important theorem related to this is what we call the uniform limit theorem. It's called the uniform limit theorem. What does it say? If a sequence of continuous real valued functions, I think this is very relevant to real analysis. Functions of a real variable. Okay, so if a sequence of continuous real valued functions of a sequence of real of a real variable is assumed to be is convergent, so converges uniformly to a limit function, then the limit function is necessarily continuous. Is necessarily continuous. Okay. This is actually one more way of constructing continuous functions, because if you are given a sequence of continuous functions, each of these are continuous functions, such that Fn converges to F uniformly, then F is continuous. So if you can take hold of a sequence of continuous functions which converge uniformly to some limit function, or rather to some function, that function is necessarily continuous. Okay. Yeah. So let's now discuss more about these continuous functions. In the next lecture, we will be studying a bit of separation actions. Right? How can we kind of separate two elements in a given topological space, or two sets in a topological space, using that topological structure. Okay. So meet you guys in the next lecture.